So we are going to talk about linear correlation coefficients R. And just like the measure of association we had in orbit contingency tables, relative risk, odds ratio, here, when we have to have a measure of association, we have R only for linear regression. It measures the strength of association between the variable x and the variable y. Just like relative risk, we use relative risk in the contingency table scenario to measure the strength of association. So here, since x is continuous and y is continuous or discrete, simply quantitative, we can use the value of, to be specific though, has to be linear association. We cannot use it for nonlinear data interpretation, but using R for nonlinear data is not good. Properties of the value are the value of R is always between -1 and +1. If the value of R is positive in the sense that it's between 0 and 1, then we conclude that there is a positive correlation between x and y. On the other hand, if R is negative, then actually we say we have negative correlation between x and y. If R is exactly equal to 0, then there is no correlation. From a practical standpoint, R could never be exactly equal to -1 or 1. It's always going to be between 0 and 1. I'll show you a case where it will be exactly equal to 1. Likewise, R will not be exactly equal to 0 in most cases, but it will be very, very close to 0. So I can draw this simple picture. Okay, there. What I'm about to say is sort of a bit subjective, but we do have tests to determine if the correlation is strong or otherwise. What do I mean by subjective? Somewhere between 0.5 and 0.8, we would say there is moderate correlation. But what I find to be moderate correlation with the value of R may not be the same for someone else, which is why it's quite subjective. But typically, when it exceeds 0.8, we have strong correlation. Point 0.8 and 1 strong. Somewhere here, moderate. Between 0 and 0.5, it is weak correlation. Same on the other side. Between 0 and negative 0.5, it is weak. Negative 0.5 and negative 0.8, moderate. And over there, it's strong. The only difference being, on this side, we have strong positive correlation. That side, we have strong negative correlation. I'm going to draw a bunch of pictures, and I want you to identify the value of R. Approximate, not exact values. So, if you have to guess a value for R, what would it be? Would it be positive or negative?
Positive.
Okay, great. What value would it, could it be? Will it be? What? Greater than 1, what is the first property that we wrote? It has to be between negative 1 and 1. It cannot exceed 1. Between 0.8 and 1? Okay, I'm going to say exactly equal to 1. That's a perfect line, do you agree? So there is no variation at all. So that is a perfect relationship between X and Y. So R will be exactly equal to 1. How about that case? Negative 1. Exactly equal to negative 1. How about that one?
0.8.
Exactly.
Oh, no, negative 0.8.
Exactly negative 0.8.
Somewhere,
right? It probably is somewhere between negative 0.8 and negative 1. And why is that? I see a line, but I do have variation, unlike those two cases. Do you agree? So these points show variability. So I have a good line, but because of the variation, it's going to be somewhere between negative 1 and negative 0.8. How about that? This one. Positive what? Oh, good.
The same thing.
What is same thing?
1 between 1 and 0.08.
Okay, so 0 less than, 0.8 less than R less than 1. It will be between 0.8 and 1. How about the next case? Do you expect R to be positive?
Yes.
Yes. Could it be close to 1? No. So what would it be?
0 to 0.5.
Somewhere between 0 and 0.5. Again, I'm being very subjective. I don't know what the exact value of R is going to be. All I'm going to say is this is weak correlation between X and Y, because I don't know the value. It could be moderate. It could be weak. All I can say is it's not strong. How about that? Is that strong negative correlation? No. So weak or moderate. How about the next one?
No correlation.
No correlations, all over the place. Last one. What do you think the value of R will be? Okay. Okay, how about this? Do you think that there is a relation between X and Y? Yes or no? Is there a connection? Yes. If you look at the underlying picture, do you agree that would be the case? So there is a relation, but I can't use the value of R. Why? It's not a line, what's your name?
Grace.
Grace. She was being very gracious. So not a line, so you cannot use the value of R to interpret this case. But if someone asked you, is there a connection between X and Y? Absolutely, there is a relationship between X and Y. Does that make sense? So what we have here is a bunch of cell phones, and do you think the first column is important? No, it's just a phone ID, doesn't matter. What do you think the second one is? The size of the phone, type of display, the talk time in minutes, resolution, and what is that? Storage, the weight. Now, of all these, which one do you think perhaps, which two variables perhaps could have an association? If you had to take a guess.
The battery capacity and the talk time, I guess.
Very good. Battery capacity and talk time. There is a possibility that they are related. How about size and weight? They are probably related too. We don't know. Let's see. You can go to graphs and chart builder. You should see something like this. So okay. Let's go to legacy dialogues and pick scatter dot. You've got a bunch of types of all types. Let's just pick simple scatter. And it wants you to define. So let's pick talk time and battery capacity. Which is going to depend on which? Would talk time depend on battery capacity, or would battery capacity depend on talk time? Talk time will depend on battery capacity. So should talk time be Y or X? Y, because Y is the dependent variable. So talk time, select, and the next one would be battery capacity, Y. You can specify markers and do other sort of stuff. I'm not going to get into all that. We'll keep it simple for this class. Also, if you go to a company or work for a company, they might have their own template. that they want. So if you select that, you can use the file that is specified, but not important in this class. It does have options. So if there are missing values, if some of the values are missing, you can make them display over here. If you want to adjust the labels, X label, Y label, whatever, you can go to titles. It says title, subtitle, footnote. You can insert those. I'm just going to give it a title, top time versus positive. 90, I'll just call it FDA 2022. Be very creative on this test. Continue. We're going to hit OK. That is the picture we get. Do you think that there might be a relationship between X and Y?
Weak.
It is probably weak. Can you see a line that can be drawn through these points?
Yes.
Yes. How about that? There is a line. It's a nice little example. In 2023, that one had a name. Outline. So in linear regression, that's what we call an influential point, because that one point could pull the line toward it because it aligns pretty much. So is there a linear correlation? Possibly, seems so. Is it going to be strong? I don't think so, maybe 0.7, 0.8. And you can see that is our title, subtitle, and the labels. So size and weight. Weight is in grams, size inches. So this is a tricky case because size can depend on weight or weight can depend on size. But which is going to be more realistic, weight is going to depend on size. Because as you increase the size, the weight has to increase, correct? So we're going to make size the x-axis. So legacy graphs, legacy dialogues, scatter, simple is good enough for us. So size would be the x-axis, weight, the y-axis, hit OK. Well, let's change the title. And that's what I get. Did we get a picture like that? Do we think that there is a linear correlation between the two?
Yes.
Sort of. I mean, I could draw a line through it, but is it going to be strong? Not sure, right? We have to find the value of R. So both the calculator and SPSS is not going to show you the value of R unless you do simple linear regression. So I'll get into it in a bit, but let's do start crunch and we'll be back to this. First, we've got to upload the data. So data load from file on my computer. Browse to the location. I have mine saved in my folder. I asked you guys to save it in downloads or desktop. So chapter 12 and cell phone specs. And upload. So when you do the homework, you're welcome to use this. As you can see, the way things are displayed here, very similar to what SPSS has. But this is more user-friendly compared to SPSS because you've got to do a whole lot of other stuff with SPSS. Let's go to graph, down to scatter plot. Of the two, which one should we pick? The first one, the X value was battery, Y, talk time. You can leave the other two as is. And it wants you to display it as a line or points. We want points because we want to see scattered points. You can change the point type, filled circle, hollow circle, transparent. It's up to you. You can pick whichever. And basic 7 colors, good enough. And that is the picture we get. So, which picture do you like better? This one or SPSS? SPSS. And of course, you can save the file and everything.
Regression.
Of all the things that you see, clearly, regression. Yes? So, and when you click on regression, you've got all these options. Which one should you pick? Linear. And it wants to know the dependent and independent variable. So we will do the talk time battery capacity one. So talk time would be the dependent variable, battery capacity, independent variable. Here in method, it says stepwise, remove, backward, forward. Forget about that. Not needed. Don't do anything because that's advanced level. So after this, we want to look at statistics that we may want. So we want the estimator and we want the confidence interval. Alex, do we remember what confidence interval is from 2023? So let's put that. And over here, modal fit is selected by default. Let's pick R squared and descriptives. Good. Continue and hit OK. Whole lot of stuff pops up. Yes. Now, it is your job to pick and choose when you write whatever report that you are intending to write. So on the side here, it is going to tell you, the title, notes, descriptive statistics, and whatnot. So the first one that you see in terms of correlations, I'm clicking correlations, the arrow popped up there, and Pearson correlation, the relationship between talk time and battery capacity is 0.431. Good. It's between 0 and 0.5. We weren't very convinced about the relationship between X and Y. Naturally, it is not the case. Also, why do we have a 1 here? Because we are finding the correlation between talk time with talk time. Yes, better be related 100%. And that's why you have 1 and 1 there. But of the two, what is important to us? 0.431. So we don't have a strong relationship. We will talk about ANOVA later. And this is the model summary that we have. You can see the R value, which is 0.431, R squared. We'll talk about that later. Standard error. And over here, where it says coefficients, you want to know the two coefficients. One is the constant, the other is the battery capacity. If you recall from last time, if I want to come up with a mathematical expression for a line, what is that mathematical expression? What equation describes a line?
Y
Y equals
equals
mx plus b. So y equals mx plus b. In our case, y is torque time. The value m is a coefficient, the slope. So it tells you the coefficient of battery capacity is 0.225. I know x is battery capacity, coefficient 0.225, so 0.225 times battery capacity. Any thoughts on what B is?
Is it the constant?
Is it?
I don't know.
It is the constant. So the intercept is that value right there, 171.583. Good, do we follow? Yes, so SPSS does everything for you. It gives you the descriptive statistics that you need. It gives you the actual model, which you can report. But the goal here is to understand what the model is about. Before we get to this, I want you to try the other example and tell me what the model is. So this time we want to pick size and weight. Regression, linear. So the weight of the phone is going to depend on the size. So options, if you have a session, it's going to be saved as is, and you can just press OK. Did it work? All good?
Yeah.
I expected it to perform worse than the other one, but it seems like this relationship is stronger than the other one. But is it great? Still not that great, but better. So here, what is the coefficient of the weight of the phone? Or the size of the phone? My bad, I'm sorry. 19.15. What is our intercept?
64.
64.113. So the weight of the phone is in grams versus size in inches. Great. We will talk about standard error and all that stuff later on, even the confidence interval. If you have your screen open, you will see the very last two columns. It would say 95% confidence interval. So first case, we had an R value of 0.431. not great with correlation. There we had 0.612. Yes.
Yes.
Slightly better, I'd say moderate. But both of them aren't that great. But how would we interpret this model? What we found here is what we call a linear regression model. Why do we call it the line of best fit? Well, out of all the lines that you can come up with mathematically, this is the line that best describes the data that you have. So when you sketch this line, that would be the line of best fit because we have an equation of love. So how would we interpret that 0.225? Got to look at the unit for battery capacity. I think it's milliamps. Yep, it's milliamps per hour. So see the unit as mAh, milliamps hour. What it simply means for every unit increase in battery capacity, the talk time will increase by how many minutes? What is that? Hector.
No.
Go ahead. You were pointing.
No,
at
it
something.
was my computer. So.
Okay. Hector pointed right here. So what did he point out? So for every unit increase in battery capacity, the talk time will increase by what amount?
225.
0.225. Does that make sense? Now, would it be practical or reasonable for me to set battery capacity to 0 and say the talk time is 171.583? Do you follow my question? Would it be reasonable for me to plug in 0 here, which means that would go away, and you will get talk time equals 171.583. Is that meaningful? Why not? Because there is no phone you're talking with, you're talking to yourself, right? Because one, if you look at the data, if you scroll through the range of data, there will be no 0 in it. 0 is outside the range. 2, it's just practical or common sense. How could you talk on a phone if it doesn't have any battery capacity, right? So is our model incorrect? No, it is correct. We just cannot put values such as 0, -1, etc. Does that make sense? By all means, once we have a model, we have to plug in numbers within the range of X values that we measured. Good. And if you scroll down the battery capacity, none of the values would be 0. There are no zeros in all those observations. How would we interpret the slope here? For every unit increase, in other words, if I increase the size of the phone by 1 inch, the weight of the phone will increase by, oh wait. 19.5 grams. So for every inch increase in the size, the weight of the phone will increase by 19.15 grams. Does that make sense? So both of them have a positive relationship. Now, this is what I want you to do. There are battery capacity values, a whole lot of them. I am going to pick 1200. Good. So I want you to find top time when x is 1200 using the first model, which is this equation. For the second data, find the weight of the phone when size is equal to 3 inches. How would we find? So I picked 1200, it is in the range of our data. So y would be equal to 0.225 times 1200 plus 171.583. And what answer did we get?
441.58.
441.58 minutes. Good. Second case, the weight of the phone and the size. I'm picking 3 inches, so weight would be 19.15 multiplied by 3. It is in the range of the data, 64.113. What do we get? Still trying. So 121.569. We'll just call it 57 grams. Great. Now, when I looked at the data and picked 1203 inches, I actually went and looked at observation, one of the observations over here, which I believe is observation number 56. Yes, that is what I looked at. For 56, 1200 is the battery capacity. What is the corresponding talk time? 430. You can look at your table if that is too small. So the actual value from the data is 430 minutes. Good. With the first model. I believe the next one was 58. The next observation that I looked at was observation number 58. Size 3 inches. Yes. When size is 3 inches, what is the corresponding weight? 120. This is our weight versus size, and that one is talk time versus battery capacity. None of them match the original value. Yes? So when I estimated, none of the values that we estimated over here match the original or actual value. The first linear model, when I used my model to predict it, I got 441.58. In reality, it is 430. These are the actual values. The second model, when I plugged it in the model, the equation, the formula, but use the fancy word, it's 121.57 grams. In reality, it was 120 grams. Yes? So of the two models, which sort of performed well?
Wait.
This model performed well, the weight model performed well, but that sort of makes sense because they are correlated in a better way, yes? Which is why it's slightly doing better. But is our method wrong because our values that we got mathematically did not match reality at all? Did we make a mistake? Or let me put it this way, is it reasonable for me to expect the exact same value from the data? Absolutely not. Reason being, that value is for one observation, that is 1200 here. But if you go up, observation number 42 is 1200 also. Yes, that's fantastic. The corresponding top time there is 420. If you go to observation number 61, the size in inches is 3, but the corresponding weight is 103. Is that close here? No. So when we change or when we estimate, we are not finding a model for each observation. Rather, we are finding an observation that represents all of the data in a better way. Now, mathematically, what represents that really well? The line that goes straight through the middle of data. Does that make sense? So this line, when you graph it, it'll cut through the data, so would the other line. So obviously, that value and the actual value are not one and the same. Do we agree? So whatever value that you get from the model is what we call the fitted value. We call it the fitted value because we use the line of best fit to get that value. Yes? The fitted value will never be exactly equal to the actual value. I should not say never. For the most part, 99% of the time will not be equal to the actual value. Good? Because our line is going to pick, or our line represents all of the observations, not just one or two. That makes sense. Okay.